Okay, so welcome everyone back to the photogrammetry course. Today we would like to extend the topics that we started to address last week in a more general setting. So the last topic we addressed was triangulation. That means estimating the location of points in the environment given we know the relative orientation of our image pair. And we looked into how to estimate, or very briefly sketched on how to estimate the location of or the positions where two cameras have been taken given a least squares approach. Just very briefly sketched that. And what we want to do today is actually put that into a general framework which is called bundle adjustment or multi-view reconstruction. And the key idea is to, at the same point in time, solve the problem of estimating the location of 3D points in the scene and the orientations of the individual cameras. At the same time, generalizing this problem from 2 images to n images. So we have a potentially large set of images taken with one camera, with multiple cameras of the same scene. And what we want to do is we want to estimate where are the individual points in the world. And we want to estimate from which locations do these images have been taken. So we kind of solve all the problems that we addressed so far at the same point in time. And this is something which is called the bundle adjustment problem, or the bundle adjustment. So what we did so far, we computed the orientation, or absolute orientation, relative orientation, but often we're interested in the absolute orientation of 2 images. And now we want to generalize this to multiple images and estimating the locations of the camera and the location of the points at the same point in time. So we don't want to decouple this process. And this is the so-called bundle adjustment approach. I will, in the first 45 minutes here, kind of introduce the bundle adjustment problem on a general perspective. What is the function that we aim at minimizing and how can we do that? Then in the second hour of today, we will look into certain properties. What can we do in order to address gross errors or outliers? And then we start looking into the numerics of the bundle adjustment problem. The issue is here that we typically face very large problems, and the question is how do we solve them in an efficient way. This is something we will probably not finish today, so we will continue with the numerics of the bundle adjustment next week. So we start, what is bundle adjustment and why is that at all needed? So my question to you is, why are we interested, or could we potentially be interested in doing multi-view reconstruction and not only reconstruction using 2 images? So what are key things that, why I may be interested in doing a multi-view reconstruction? Because it's mathematically more complex, so what could be a reason for doing that? Ja.
Ja, das ist ja sehr praktisch, wenn man von der gleichen Situation mehrere Bilder hat, dann hat man halt mehr Informationen und dann sind auch die verschiedenen Ungenauigkeiten kleiner.
Yeah, absolutely correct. So if I take multiple images of the same scene, I have the potential of having a more accurate estimate of the point locations, for example, that I want to measure. What could be another motivation for doing that? So why may I be interested in doing that? So what happens if we have more complex geometric shapes?
It might be that from a little number of viewpoints, I cannot see all the details of my object.
Exactly. So if I have a complex geometric shape, I may need a large number of images in order to do a full 3D reconstruction. You can see that if you just want to create a model of yourself, for example, and you just have 2 camera viewpoints, you want to reconstruct the 3D points of your body surface, it is not sufficient to cover your body. So you will need multiple viewpoints in order to do a full 3D reconstruction. What could be other relevant aspects that I may be interested in?
Maybe also to cover changes over time.
changes over time is something which is definitely relevant, but that's something we are not going to address here. So we assume so far that the location of the points that we observe do not change. Otherwise, the problem gets substantially more complex, but doing then this mapping or reconstruction in dynamic environments is definitely a research topic and a relevant topic, but it's nothing we are going to address here. So it can also be relevant if I want to have a level of detail in my reconstruction that I would not have if I observe the scene with one single image or with a pair of images. So consider you want to build a map of North Rhine-Westphalia and you fly with an airplane over the country and you take images. Either you're flying very, very high, then you may make 2 images of North Rhine-Westphalia and do a 3D reconstruction, but this often doesn't give you the level of detail that you want to have. So you will fly lower and then you just stack multiple images together. And of course you want to have a consistent estimate of the map that you're estimating. And the last point, you may be interested in estimating also the position of the vehicle, of your airplane, of your car, of your robot, whatever it is which carries your sensor at different points in time, because you're interested in the location of the vehicle in relation to a map that you build online. And that's something which is also called the simultaneous localization and mapping problem, where you want to estimate at the same point in time a map of the environment, that means reconstructing the 3D points of the environment, and localize the sensor in the environment, in this map that you built. So bundle adjustment problem is basically a visual simultaneous localization and mapping problem. So often the simultaneous localization mapping problem is slightly more generally formulated with using different sensors, whereas bundle adjustment is designed for using cameras. Okay, just an example of how such a bundle adjustment system may look like. So what you see here is image footage taken from a car. So there's a car equipped with 8 cameras. This is a company, it's a spin-off of KU Leuven called GeoAutomation, which basically do vision-based surveys. And what you see here are 8 cameras that record image data from a car. So they kind of 8 cameras, 2 in the front, 4 to the side, and 2 looking to the back. And what you see here on those sides are actually the 3D points which are generated from those images. So this is kind of how the cameras are installed on the van. You can now drive through the environment, record camera data, estimate the 3D location of those points, and at the same point in time build a map of the environment and locate your cameras in the scene. And if you can do that on a large scale, you can zoom out in this example over here, and you can actually see that you can construct a city-scale map using this approach. And it's just generated by a survey vehicle equipped with cameras driving through the scene. Of course, in order to get kind of a globally consistent model, you will use additional sensor information. So for example, GPS information is used in such settings in order to compensate for drift, in order to align, in this case, the underlying map with the model that you can build. So you will use additional sensors. You may also exploit the odometry information of your car. So you're basically, from the speed of the car and the steering angle of the car, can get an estimate where the next pair or 8 camera images have been taken. You can actually zoom in again into your model and go back to these point-based representations. So these points are the points scanned from the environment. So you can see that this approach relies on texture. So the reconstruction of the environment relies on texture because on the kind of the dark areas of the road, there are basically no points. So you can guess sometimes the lane markings. You see the curbs, there's some texture whenever there's something green, or you see a house or kind of the lane markings down here. You can roughly estimate them, but you can also see or hear buildings that whenever there are textureless areas, you will not get a reconstruction of those points. And one of the reasons for this is that the feature extractors, so those extractors that generate hypotheses for corresponding points in your images, will not detect any, let's say, distinguishable feature or well distinguishable feature. So if, for example, see a white wall, your feature detector will have a very hard job to find a a feature point on this white wall and is able to find the point in the second camera image so that they overlap because there's no texture. So you need a lot of texture in order to do that. And given we extracted those corresponding points in images, so still with an assumption that we are relaxing this in the next weeks towards Christmas, so we are still assuming we have those corresponding points. So we know that a point that we see in camera image number 1 corresponds to another pixel location in camera image number 2, and so on. So generalize this to n images. So we assume to have those corresponding points. The question is, how do we estimate such a 3D model giving those corresponding points? We do this for n images. And again, as I said, the approach that we are using is called bundle adjustment, or originally called bundle block adjustment, although nowadays most people just call it bundle adjustment. So the idea is to use a least squares approach for estimating the location of the 3D points in the environment and the orientation parameters of our camera at the same point in time. And the orientation parameters of my camera may not include only the exterior orientation, it may also include the intrinsics. So if we have the same camera and the camera calibration does not change, we can typically assume it to be constant and estimate it over the process being the same for all images. But there may be other setups where I use multiple cameras or let's say downloaded images from Flickr of a place and want to do a 3D reconstruction based on those images. That's something which is possible today. Then of course you have to deal with individual calibration parameters for all the individual cameras. Okay, so where bundle adjustment originates from is actually from building maps using cameras from aerial images. We have an airplane, we fly over a scene, we take images. So this is an example of 6 images taken of the scene. These are kind of the projection centers of my cameras. And we have a couple of points on the ground. We want to estimate the location of these points on the ground. In order to relate them to a world reference frame, we typically have something which are called, these guys which are called control points, something we discussed already last week. This is an example. This is a control point, and this is a control point. These are points in the environment for which the 3D location is known and is often assumed to be perfectly known. And we need this information in order to relate the coordinates of those points to an external reference frame, so to the world or the object reference frame, and we also need it in order to fix the scale issue that we have, so that we can estimate the location of those points only up to a scale. So in solving this problem, something called aerial triangulation, and this is kind of where the bundle adjustment was developed in this context, originated from, that we fly with an airplane over an environment, take images and want to build a 3D model of the ground. And today you find automated software packages which actually do this job for you. So given you have those aerial images, you can put it to your bundle adjustment software and it would actually generate you a map of the environment with 3D locations. So always the question how well those system works depends on the quality of your sensor data, which assumptions are made, which external information you may have, so you can generate very, very high quality reconstructions, but in very challenging settings. So depending on how fast the camera moves, what camera movements are considered, what is the movement direction with respect to the camera, what happens about lighting conditions or changes in the environment. These are all things which may break these automated softwares, and this is why there's still research ongoing in the context of bundle adjustment or what's called visual simultaneous localization and mapping today. So this was kind of the very high-level overview about bundle adjustment, what it's there for, and why we may be interested in that. And now I would like to dive slightly deeper into what is the kind of the function or the underlying principle of the bundle adjustment problem, and then look, how do we ensure that we have our problem well formulated so that next week we can then look into the problem, how can we efficiently solve the bundle adjustment problem and solve the underlying least squares problem. So are there any questions up to this point? Was kind of the core theme clear for this course, for today at least? Okay, so let's go slightly more into the details. So if we look to the underlying basic equation that is related to bundle adjustment, we'll actually find this equation over here. So what we see here is, what we have here are the points of my camera, the points, the coordinates in my images that I measured of a point I in an image J. So we now have a potentially large number of images. So J refers to the image. I take my first image, J is 1, second image, J is 2, third image, J is 3. And I indexes a point which I would take in those images. I have multiple points in my images that I observe. And the A here means that it's kind of an arbitrary coordinate system. Arbitrary in the sense that I don't want to restrict this to calibrated cameras. So we may be calibrated, we may be uncalibrated. We have some reference system of my image, and it's not necessarily a calibrated one, but I'll keep this A for arbitrary over here. Then we have our corrections or improvements that we have here. So ij, point I observed in image J, and the corresponding correction. And this is all in homogeneous coordinates. So given this type of font indicate that these are homogeneous coordinates. And this should be equal to, let's start from here. This is the 3D location of the point I in the world. So where is this point I in our world? And this is mapped into the camera image through this projection matrix over here. This projection matrix is a different one for all individual images because they have been taken at different locations. And it depends on a couple of parameters. So this parameter set P, this vector P, are the projection parameters which are used. For example, the rotation matrix of our camera, or the camera constant, the intrinsics and the extrinsic parameters. So this is typically an 11-dimensional vector, first with 6 parameters for the extrinsics and 5 parameters for the intrinsics. And we have additionally this parameter Q. The parameter Q encodes the nonlinear corrections that I may need to apply. So if I have a radial distortion, for example. So we very briefly discussed this in Photogrammetry I in the context of camera calibration, that we may have additional parameters here which are those which perform a nonlinear correction on my image. And this correction may depend on the location where this point is mapped into the image. Of course, for example, there may be a correction which takes into account how far the point is away from the optical axis. Therefore, I need this parameter as well in here in order to do the correct undistortion of the image points. So it's what this approach does, it maps my point from the 3D world into my camera, the arbitrary reference frame in my image plane, typically. And I have a scaling parameter in here, and the scaling parameter here results from the homogeneous coordinates. So because they're only determined up to a scale. So these are those guys over here. I have a scale factor, the calibration matrix, together with nonlinear calibration parameters, and the 3D point, encoded again as homogeneous coordinates. And what I have the uncertainty of the measured image coordinates in my image. So I assume to know the noise involved in measuring a point. So I can, for example, estimate the location of a corresponding point up to whatever, half a pixel or something like this. So this is the information that I encode in here, and that may be different for individual points or individual images. So some images may be more blurry. So even if I measure the same point in image 1 and image 2, and image 2 is blurry, I may have a higher uncertainty in image number 2. Okay, and here we have the uncertainty of the image coordinates and the points in image J and the number of images that we have. Okay, is this equation kind of clear what it is doing? So it's basically the process of how my camera projects a point from the 3D world into the camera. And this equation actually encodes two things. It encodes the projection from the 3D world into my image coordinate system, so the arbitrary image coordinate system that I may be using. So this was kind of probably rather clear from the equations because we have our projection matrix in here, and you know how the projection from the 3D world to my camera frame works. The second thing, which may be not extremely obvious, is that it also encodes the coplanarity constraint. So why is this the case? So something which originally encoded sort of using the fundamental matrix and how the point is actually mapped. Why is this encoded in here as well? So it is encoded because I'm observing the same point in different images. So I'm observing the same point in different images, and they are all mapped to the two, and only if this kind of the estimate of this location is correct, those points will actually be mapped to the same pixel coordinates. So if the location of a point is wrongly estimated, I'm expecting to kind of project the point through this equation to a wrong location in my image. And if I would be projected to the wrong location in my image, I would get a large error over here, and I'm trying to minimize this error in the end. So what I'm doing with this equation, if I kind of minimize this, I minimize the reprojection error. So which error do I get if I take the point where I estimated it and project it back into my image? So the question is, what are now the unknowns that we have in here? So what are the unknown parameters? The first thing is we have the 3 location of our new points. So these are these guys over here, location of the point that we have, and this is what we want to estimate. So we want to estimate where is this point in the 3D world. And if I project this 3D point in the world through my projection matrix, I should end up at a point which should be in line with where I observed that point. Then I have this one-dimensional scale factor. I have 6 parameters for the extrinsic, so the exterior orientation of my camera, and this is dependent on every image. So every image has an own exterior orientation because the image has been taken from a different location. We then have our intrinsic, so our linear camera parameters. And again, if we assume to have the same camera or the scene is recorded under the same conditions, we can assume this to be constant over the whole data set of all images. If we have changing conditions, this can change, for example, if we fly with an airplane and a camera under different or substantially different temperatures. The temperature may change the calibration parameters of my camera, for example, the camera constant. And then I may need to take into account that these parameters could change. Or, as I said, the example I used before, if I take a collection of images taken from the internet, let's say I Google for whatever, Münsterplatz or Rathausplatz in Bonn, I take all the images that I find on Flickr and try to do a 3D reconstruction. I can do this, but then I need to take into account that every image has probably a different calibration parameters because they've been taken from different cameras. And so depending on the setup that I'm using, either these are 5 parameters or these are 5 parameters per image. And I have additionally nonlinear distortion parameters, which are always taken into account. These are the unknowns. Actually, quite large number of unknowns, given that I may have a large number of points, a large number of images. And this can be or could be problematic later on. So are kind of the unknowns that we have clear. So we have the 3 location of the point that we want to estimate. We have this 1D scale parameter, which comes from the homogeneous coordinates. We have the location of the camera for every image individually. We have the 5D intrinsics, the linear parameters of my camera, which is often assumed to be constant over a data set, and the nonlinear parameters, which are also often assumed to be constant over the whole data set. So these are parameters which often occur only once for every image, for every point, and every point and image. Okay? So all the unknowns are clear.
Yeah. Why
So if we look to this equation over here, so it's clear that if we are in homogeneous coordinates, we have this scale ambiguity. So the homogeneous coordinates are only defined up to a scale parameter. And this projection matrix also differs for every point because the nonlinear correction parameters differ in here. And so we have an individual scale parameter for every pair of point and image. So every point may have a different factor over here. Okay, we can, again, split this up into this projection matrix, for example, into two terms. So we have the calibration parameters, so these are then also only the intrinsic parameters, and the extrinsics sitting over here. The rest is basically the same. Which leads to the next question. If we have this equation, how many unknowns do we have? How many unknown parameters do we have? So if we have an example, let's say we have 10,000 images taking over the same scene, and we have around 1,000 images, points per image. So new points that are not control points. And we assume on average that every point has been seen 10 times. So some of the points may have been seen a bit more often, some not that often. So the question is, given my equation over here, how many unknown parameters do I have in this setting? And how many observations do I have? So what is the number of observations in this setting? Yeah?
1,000 points times 2 coordinates.
So 1,000 points times 2 coordinates. Yes. 2,000. And what else do I need? So that would mean I observe every point only once.
This times the number of images.
Yes, exactly. Times the number of images. So we end up at 2 times 10,000 times 1,000. We have 20 million observations. Which is already a quite large number. Given that 10,000 images may sound large, but it's actually not too large.
Why?
Because we observe the x and y coordinate in our image.
Okay, so we call
So,
each coordinate.
yeah, so because we observe them individually, so we observe them individually, and therefore there's an individual observation. How many unknowns do we have?
So we have 1,000 points, and each point has been seen 10 times, so it should be 100 points.
So we see 1,000 points per image.
Oh, yeah, so times 10,000.
Yeah, exactly. So we are ending up having 1 million points. Okay, so we have 1 million points. How many unknowns does this generate for us?
3 million.
3 million points, exactly, because they have an x, y, and z coordinates that I need to estimate. Okay, so 3 million unknowns just from the points for this guy over here. What else do we have? So what about this matrix over here? How many parameters do I have in here?
60,000 extrinsic, because we have 6 extrinsics per image.
Yes, exactly. Yes. 6 extrinsic parameters per image, 10,000 images, 60,000 dimensions. And the intrinsics?
We have the same camera, it's fine.
Exactly, just 5 and maybe a few more for the nonlinear ones. So that's actually a neglectable number. And I have this guy over here.
We have this guy once per point, right?
Per point and image. So which adds another 10 million unknowns to the process. So we end up in sum of having 2 times 10k times 1k, 20 million observations, and 1 million points with 3 degrees of freedom, 10 million for the scale, and 1,000, so 6,000 orientation parameters in the intrinsics I can completely ignore. Oh, they actually, that's actually wrong. This must be 10,000 because we have 10,000 images, so this must be 10,000 over here. Sorry, so this must be 10K orientations with 6 degrees of freedom, not 1K. But anyway, this is just a few thousand more. So in the end, we end up with having something like 11 million unknowns, approximately, and 20 million observations. That's a pretty large number. So the first thing is actually, can we reduce this? Can we do better? And one thing we can do is, we can eliminate the scale factor. And the scale factor, so this scale factor which only results from using the homogeneous coordinates. I can simply go back to the Euclidean space because then I get rid of this scale factor that is individual to every point. I mean, I still have the issue that my final point cloud is only determined up to a scale, but I don't have the parameter for every mapping individually in here. So I can simply do this by going from my homogeneous coordinates to the Euclidean coordinates, therefore the change in font over here. And then I simply I perform this projection, basically take the first 2 dimensions and divide it by the 3rd dimension. So this is normalization which comes from the homogeneous coordinates that I need to normalize the resulting vector that I get. So it's kind of this short way of writing it. So this will boil down to a 2D Euclidean vector over here in my image. And in this way I multiply and divide by the scale factor and get rid of the scale factor. Just by going to the Euclidean coordinates. And through this normalization, I get rid of the scale factor. Which is good, because this reduces the number of unknowns that I have. So you have 10 million unknowns less. Go from 11 millions down to 1 million. Which is a very, very big improvement. Just by using different coordinates. So far the homogeneous coordinates served us very well, because a lot of things are easier, but sometimes it's easier to change back to different coordinates if this simplifies our problem. Okay, now I have my standard equation that I can use for solving the nonlinear problem that I have. So it basically boils down to setting up the system of normal equations. I have my unknown and my observation. So on this slide, I know it's slightly misleading, but the observations are x because this corresponds to those points over here. And the unknowns are u. So I just used it on this slide. So in the end, I go back to the standard notation just to make sure that the point that we observe are the x are the point that we observe, and u are in this case the unknown. But it's kind of the standard procedure how I compute the updates for my unknowns, and I need to iterate this process because the projection is a nonlinear mapping, right? So we have nonlinear functions involved, we have the rotation matrix in there, so it's a nonlinear process, so we need to iterate this process over and over again. Assuming that we can solve this system of linear equations, we can iterate this process, we're actually happy, we come up with, we can compute the updates of our parameters and then of our unknowns, and assuming we have a good initial guess, we will converge, or hopefully converge, to a solution which then tells us where are the points in the 3D world and where are the cameras looking to, so that I can have all unknown, and also the calibration parameters of my camera, so that all unknowns have been determined. Okay, so in order to relate this to an external reference frame, we also need our control points. And so some of the points that we are observing are probably, or we will probably enforce this, are control points. So the problem is now, so far I treated all points, or all observations, as noisy ones. So if I have control points, which I have, for example, which Heiner-Kuhlmann's group has determined their location for me for some control points on the ground, and I'm flying with the airplane over Bonn and want to do a 3D reconstruction and can identify the location of the control points on the ground, which are measured with a very high precision. So should I take them into account? Yes, I should definitely do that. But the question is, how should I take them into account? Should I take them into account as God-given? So not going to change. They're never changing. Or I can assume, maybe someone made a mistake and they are noisy. What are pros and cons for taking them into account as noisy and taking them into account as noise-free?
So we normally take them into account noise-free because it's easier for us to compute their standard deviation. If we think the standard deviation of a Stützpunkte are 0.
Yes, we can do that. That's one reason why I may want to do that. Or there are other reasons why I would like to do that. There are more reasons.
They should be much more accurate.
Yeah, so they're definitely more accurate, but even if I say they are 100 times more accurate, I could take that into account in my standard deviation, so that would not be a problem to take that into account. So you're more on the side, you say we should treat them as noisy, although the noise is comparably small to the point that we are observing.
But maybe because it's the only connection to our reference frame.
It is the only connection to our reference frame, that's true, but if this connection is noisy, I could argue I should take this noise into account. So there are arguments for both sides. So on the one hand side, I say, if the points are noisy, I should take the noise into account in order to obtain the statistically optimal solution. So I may want to update the location of my control points. Typically, the update won't be too large, but I may take that into account. This could also allow me to do things like check for gross errors. So maybe there was a gross error or an assignment error between the control point and what I'm measuring, or when measuring the control point, so that there may be outliers in those points, and I may be able to identify them, using the additional information that I have from my camera information. On the other hand, if I want to relate the map that I built to an existing map or other maps that I have, which are taken with respect to those control points, I don't want to change those control points. So typically the constraint in the application will say keep the control points fixed and don't change the control points. But if I want to create the statistically optimal solution given the observations that I have, I should consider them as noisy. And that's actually quite easy to do. So I have my provided coordinates, I have a correction, and I have my estimated coordinates. And there is an uncertainty on how accurate the provided coordinates actually are. And so the uncertainty of the provided coordinates is in general much smaller compared to the point that I measure. But I can take that into account. So, but again, they are depending on the application that I have, I may take them into account or I keep the control points fixed. It simply depends on what I need to do. What it often can do, one basically does two steps. In the first step, I consider those points as noisy. I do the statistically optimal solution and I also estimate the corrections for the control points. And then I say, okay, are those control points in line with what I measured? And I do a statistical test on that. And I do that in order to identify outliers, to potentially say this control point, there's an outlier, either in the correspondence that I have, I may revisit the correspondence, or if the correspondence is fine, maybe there has been an error in my control points. So and then I eliminate those control points which I identified as having gross errors, and then I do the bundle adjustment again and keep the control points fixed if I need to relate the model that I built, for example, to an existing map. So in this case, I have a check that those control points don't screw up my bundle adjustment solution, in the sense that I eliminate potential gross errors. It shouldn't be in there, but you never know. And then I can keep that fixed if I need to have if I need to keep the control points fixed, if I need to relate my map to those kind of God-given control points. So I use the fixed control points to enforce a match of the geometry that I estimate and the geometry that is kind of given to which I should relate my model to. But you also always should take into account that this is a suboptimal approach if we see this from a statistical point of view. Because from a statistical point of view, we should treat them as noisy measurements if they are not perfect. And given the new observations that I have through my cameras, I can improve the estimates of those control points. But given that I typically cannot change the control points, if I cannot change them, I need to keep them as fixed. But this is a statistically suboptimal solution from a statistical point of view. Okay, so what we have done so far is kind of introducing bundle adjustment as we have an equation and we try to minimize this equation. So we try to find the corrections so that we come up with our estimate and are able to update the unknown parameters in order to estimate the 3D location of our points and in order to estimate the orientation parameters of all my cameras where the images have been taken. And we did a few considerations of what should we do with our control points in this setup. We haven't talked about things like how good is my solution. We haven't talked about things how to identify gross errors. We haven't talked about things like how should I solve this potentially large system of linear equations. That's something which will follow in the next hour, but if there are no further questions at that point in time about kind of the more general approach, we could make a 5-minute break and then continue with the second part, which will then look into key properties of the bundle adjustment problem. So are there any questions at that point? If this is not the case, make a 5-minute break and then we're going to continue. Thank you. Okay, so in the next 40 minutes, 45 minutes, I would like to look a little bit into what are different properties of the bundle adjustment solution and what can we tell about the result that we have, or how can we evaluate if our result is, for example, good or bad. So the first thing, and this is kind of one of the important things, is regarding optimality. Of course, we are always interested in finding optimal solutions. And from a statistical point of view, bundle adjustment provides me an optimal solution to the problem of estimating the location of my cameras and their orientation and the location of the 3D points in the world. That means that we take into account all the involved uncertainties. So we have an uncertainty, for example, in measuring the pixel coordinates of corresponding points. And I can take this into account as well as I could take into account all correlations between the measurement that I have. I come up with all the information that I'm interested in with the highest possible precision under the assumption that I don't have gross errors and my points, all the distributions which are involved are Gaussian distributions. And what we also do, we require an initial guess. So because we have a nonlinear estimation procedure. Given that we converge, we start not too far from our initial guess. We'll come up with the statistically optimal solution, but the question is also how can we make sure that there are no gross errors, and how do we obtain an initial guess? So two things I need to care about if I'm talking about the properties of the bundle adjustment problem. So the first thing we need to find out what are reasons for gross errors. So which reasons for gross errors can you imagine? Yeah, wrong corresponding points. So this is one of the key reasons for gross errors. They can result from the fact that I automatically extract features from my camera images and relate those feature descriptors with each other. And they can simply be the same object in the environment, which appears perfectly identical. And this can lead to wrong data associations. So if you consider the building we are in here and the building next door actually the same buildings. Of course, the surrounding is slightly different, but if I just have images from a partial view of the facade, for example, it's very hard to distinguish that it is Nussallée 15 and not 13 because the buildings look the same. So just because there are different objects in the real world which look the same, I can obtain wrong corresponding points. May also be that my feature descriptor is not expressive enough to separate two points which for us as humans look completely different, but from the feature descriptor point of view may look the same. So I may also get wrong data associations or wrong correspondences due to that. But this is kind of the main source of error, are wrong correspondences. Because, of course, they will introduce a very, very large error if I say I'm here and observe a building, and there's a building in downtown which looks exactly the same. I would have corresponding points between those two buildings, but those buildings are in reality very, very far away. So this introduces very large errors. What are other reasons for substantial errors that I may obtain? That's absolutely a valid point. If I have dynamic objects moving through the environment, especially if you think that I'm observing, taking measurements, let's say, from a car driving through the city, there are very likely to be cars in front of me, and we will more or less drive at the same speed. I will reobserve the car over and over and over again. And the approach that I've represented so far simply cannot or doesn't model the fact that the objects or the points can actually be moving. So they can be at different locations at different points in time. Something that we completely ignored, and we still completely ignore, but this is in practice a reason for wrong data associations that I need to handle. And the other thing is that I simply have wrong point measurements, although just by wrongly measuring the points in my image, this doesn't cause that bad errors typically. There's the completely wrong correspondences. So the question is then, how many observations do I need per point in order to identify, or let's start, how many points do I need to estimate the coordinate of a 3D point? So how many observations of a point do I need to estimate the 3D location? 2 points. I need to see the point in 2 camera images from different locations. Via triangulation, I can estimate the location of the point. How many observations do I need in order to identify that something may gone wrong in data associations? So I have a third observation of that point. I can check those guys pairwise and see if they all provide a similar result. So with 3 points, I may have a chance to say one of them may be wrong. I can't tell which observation is the outlier, but I can do that. If I have 4 observations per point, I assume that there's one outlier in there. I can actually identify which of the measurements is wrong. In general, we typically say if we have 5 to 6 different observations per point from substantially different viewpoint locations, I typically get a precise estimate of the location of this point. So this is basically a rule of thumb. So if you've seen the point from 6 different images, and those images have been taken at substantially different locations, I should actually obtain a good estimate about the location of this point. Of course, the exact uncertainty of this point depends on how accurately I can actually measure the point, where the point in my camera image, what the uncertainty of my orientation parameters, all those things matter. But if we have, with the rule of thumb, let's say 6 observations per point, we're typically good. So then the question is, how do I eliminate those gross errors in practice? And how do I actually obtain also an initial guess? So what typically do given that we have this large set of images, we actually break down all the images into small chunks of images. Let's say I take 3 to 6 images and decompose the overall problem in terms of optimizing all whatever n or j images into first addressing small blocks of images. And of course, I assume the camera is moving, so I'm moving the camera through the environment. They should have seen more or less the same scene or a very similar scene. And what I then can do is I can look for corresponding points, and I check, use it based on the feature descriptor, based on the constraints that I may have, for example, from estimating the fundamental matrix or the essential matrix incrementally between those images. I can try to identify wrong data associations in my observations. And I simply eliminate those gross errors and compute a solution, and then I can even compute a solution for the small observations, and in the end solve the full bundle adjustment problem. So there's one way for kind of see this as a pre-processing step to get rid of my of a couple of gross outliers that I have. And I can also use this in order to check the observation that I get, so the observations in my camera image, with my control points. You see if they are maybe either wrong data stations or errors in my control points. So the next important question is, after I identified my gross errors, is how many control points do I actually need? So if we look to the existing solutions that we have for relating point that we see with an existing coordinate system through control points, we either use the DLT and required 6 control points, or the projective 3-point algorithm where we required 3 or 4 control points depending if I want to resolve an ambiguity or not. and I need that for pairs of points. Sorry, for every pair of images, not pairs of points. For every pair of images, I need to see those control points. Otherwise, I can't compute the DLT or the projective 3-point algorithm. So the question is, how many points do I need for the bundle adjustment problem? Any idea? So I need a substantially small number because I only need a small number of control points for the overall problem. It's very hard to give the very perfect statement, I only need 3 or I only need 4, because what in practice can happen is it's not always guaranteed that I can estimate, so the chain of observations can actually break at some point if I have no overlaps or don't find any corresponding points. So I may need to observe in different chunks of data different numbers of control points, and depending on where the control points are located in the environment, some part of the scene may be affected with a very large uncertainty. Given that the bundle adjustment typically spans over a large area, I cannot say 3 are always enough or 4 are always enough. Typically but I need a substantially smaller number than 3 per image pair. So if you consider that if we do the relative orientation of 2 images, let's say I have 2 camera images, one taken here, one taken here, and I have my control points, let's say somewhere over here, I can perfectly estimate that. If I start with this, do a bundle adjustment, and take a lot of camera images here all over the scene, and I have whatever, 10K images recorded up to here. Using only these control points over here, let's say a few more, may be highly suboptimal for getting a good estimate of those points over here. So I may want to distribute a couple of control points all over the place. But that's actually something we are going to discuss next week as well, where I should place those control points. But the important thing is I need a substantially smaller number of control points. And what one typically does, one places those control points at the boundary of the area that I'm mapping. So if I map the whole blackboard, I kind of make sure that at the boundaries I have a couple of control points that I know, and then I should be actually pretty good off. And reducing the number of control points that I need is actually one of the big advantages of using bundle adjustment and doing a multi-view reconstruction rather than doing reconstruction from 2 views. Because then I can only take images where I see a sufficient number of control points. And this is something that the bundle adjustment relaxes. Okay, so we talked a little bit about removing outliers, and we talked a little bit about control points for bundle adjustment. So the next thing is how to obtain an initial guess. With the least squares approach, we need to iterate, so we depend on our initial guess. The problem that we actually have is that for our pairs of images for computing the relative orientation, we had our direct methods to compute an initial guess. So given that we have 2 camera images, we actually can obtain an initial guess of their relative orientation. The problem is there's no direct solution known for the n-view problem. So if you have a larger number, whatever, 10 different views, there's no direct solution that we can actually compute to do that. So what we need to do, we need to have some other means for finding an initial guess. The question is, what could be ideas for finding an initial guess? Any ideas what we could do? first thing we could do is if we treat our images as being recorded in a sequence, I could relate image 1 and 2, is computing the relative orientation, image 2 and 3 compute the relative orientation, 3 and 4 compute the relative orientation, kind of chain those relative orientations. That's one thing I could do. The other thing I could do, I could just compute the relative orientation between 2 points, two images, estimate the location of new points that I see in the environment, and use them as control points for the next step, for relating the third image to the previous one. And then estimating again the location, taking those as new control points to compute an initial guess. There's another alternative that I can do. What I also can do is I could take additional sensor information into account. That's something which happens often in practice. So if I have those cameras on my car, first those cameras are rigidly mounted with respect to each other, and I typically have access to the speed and the steering angle of the car, which gives me an idea where those cameras are located in the 3D world, and even tell me something about the scale, because it tells me with some uncertainty how the camera moved. It's something which I need to incorporate into this process if I want to use. So either I use it in the bundle adjustment, then I need to incorporate it into the process, or I just use this kind of odometry as an initial guess for the camera locations, and via triangulation can then compute the location of the 3D features as an initial guess for the bundle adjustment solution. So different ways different approaches that I can take depending on the information that I have. So do I have this odometry information, yes or no? Do I know that it was a sequence of images, or is this a random collection of images? This all changes how I have to build up my initial guess. So if I, for example, have random collections of images, really one way is to simply look for similar looking objects, relating those objects as corresponding points, and then computing the relative orientation between the individual images. That would be one way, which could give me an initial guess. So if I take the idea that I mentioned before, that we take the first 2 images to compute the relative orientation, then via triangulation we can estimate the location of the points in the scene, and then we can use the projective 3-point algorithm to, or the spatial resection, this is 2 words for the same thing, to kind of estimate the location of the subsequent images. So do you see any problems with this kind of approach? Any problems if I do that? So for the first 2 images, I compute the relative orientation, then I can nail down where the points are. From the next image, I take them as control points and estimate where they are. Yeah.
When our first image pair is a bad pair, I would say, we have a bad relative orientation for all.
Yes, that's one point, important point. Also, even if we do it very good, so we have a very good initial estimate.
I think error propagation might become a problem.
Yes, this can turn into a problem. On what does this depend on? How large the error grows? It could depend on.
Well, how many images you make before you can do a double check with one of the later corresponding points, for example?
This is one thing, and the other thing also depends on how many corresponding points do I actually find, because I need a substantial overlap between all sequences of images to do that. And so if I have a large number of points that I see, and there's a very large overlap in the viewpoint between consecutive images, this may be fine. If not, I run into problems. Also, outlier handling is very critical. Other things that we have is some of the direct methods that we used have problems with some configurations. For example, for the DLT, all points should not lie in one plane. What happens if I move in front of a wall, let's say even if the wall is perfectly textured, I have whatever posters on the wall, and I just move and observe this wall where all points lie on a flat surface. And I can't recover those locations. So there are different problems that we can encounter if we use this as a technique for generating an initial guess. So there are different techniques that I may combine to come up with a good initial guess, and the other thing is using additional information that I may have. So if I'm flying with an airplane, I have the speed of the airplane. If I'm driving with a car, I have the speed of the car and the steering angle. Maybe I have GPS information, which you can see as putting a control point into the camera, a location of the camera, which of course helps me to dramatically simplify the problem and come up with a pretty good initial guess. These are different techniques that I may be using for computing initial guess. Yes, please.
Point of critical issues required enough points per image overlay.
Yes.
Yeah.
Points.
Doesn't that contradict the statement you made a few minutes earlier that with this bundle approach you need much less control points, but because now it looks like, well, you need quite a number of control points.
Okay, so these points are new points, not control points. So if I have two consecutive images and I compute the relative orientation, I compute the location of the points in the 3D world given those two images, and then take a third image. And then I kind of use those points as fixed and compute what is the relative orientation from 2 to 3. And then I can take all points into account which are new points, which I can assume to treat like control points to estimate the location of this camera. That's how this was meant. So requires enough new points or non-control points otherwise that would eliminate all the advantages from the bundle adjustment if I would have enough control points. Not all advantages, but eliminate one of the key advantages that we discussed before, that we only need a small number of control points for bundle adjustment. Any further question at that point? Okay. So bundle adjustment is one of the approaches which has been around since quite a while and is one of the absolute standard techniques used in photogrammetry. And it's one of the things where you can find existing solutions. There's commercial software out there which you can use, for example, if you have whatever, buy a small helicopter or drone, put a standard, whatever, GoPro on that camera, fly over a scene, and you can actually use this information, putting it into standard software you can buy in order to build, to solve the bundle adjustment problem, come up with a map of the environment. And they do a lot of techniques that we have discussed here in the course. So one of the things is you need to estimate relative orientation between, to actually track the location of the vehicle for an initial guess, which is typically done using the 5-point algorithm or maybe the 8-point algorithm, together with the technique, with the ransack technique, so rejecting outliers. You need to put that, you need to find corresponding points, eliminate potential wrong corresponding points, so those pre-processing steps, and you in the end put this into a bundle adjustment solution. You may additionally take into account some gyros that are installed on that UAVs to get a better estimate of the relative movement of the platform, to get an idea where those images have been taken, or additional sensor information, GPS information maybe into account. But the existing solution often allows you to build quite accurate maps of the environment using standard components, standard hardware. What is typically not automated if you have existing ground control points, you still need often still need an operator that creates the correspondence between the measured ground control point, which has been measured with external sensors, and the locations in the images. This can be one source of errors for making wrong data association, but this is a process which is typically done manually. The rest is a more or less automated process, maybe with some manual checks, but most of the components actually run as a batch process. So next thing we're interested in, once we have done that, what's the quality of the solution that we get out? So even for computing the relative orientation, we looked into different things like this Gruber points or Gruber double points to get an idea what is the relation or the quality of the solution that I have. The problem is for bundle adjustment it is not that easy because we typically have larger scene, we have a large number of images, we cannot make the assumptions that we used in order to evaluate the quality of the solution for the image pair. So there's no standard approach of this is the accuracy or the quality of my solution that I get. There are, however, some hints that I could use in order to check, are my results right? Is there a big mismatch between the model that I assumed and the results that I get? The first thing is I can actually look into the variance factor and ask myself the question, is the variance factor far away from 1? Or does it take values around 1? So if the estimate of my variance factor is around 1, it's a pretty good idea. Well, I get an idea that the assumption that I made in my model seems to be correct. And one of the things I can do is I can actually apply a statistical test to estimate the to get an idea how far it can actually deviate from 1 and still have potentially a correct estimate. So one of the problems that I run into in this kind of setting is given that I have typically a large number of observations, so a high redundancy in this system, that statistical test that relates my estimated factor and the one I want to obtain, so the uncertainty of the observation that I estimated, and so the relation between them is given through the variance factor. With a statistical test like an F-test, I typically have very high redundancy values, and this uncertainty here basically means that I know this value is kind of the true value. So if I take a small example, let's say I assumed I have an uncertainty of how accurately I can actually nail down a corresponding point. I assumed it to be 0.5, and according to my process, I estimate as 0.35. And the redundancy, and I have a redundancy which is rather high because of a high number of observations. If I would apply a standard F-test to do this estimation, and I would actually get a quite small value in my table and actually would reject the test. And the problem that I have in here is that in the F-test, the infinity that I have here is assumed that the parameter that I assumed in my model is a correct parameter. So basically, say I assumed this to be the variance or the uncertainty with the standard deviation. So the uncertainty, how accurately I can measure a point. What it doesn't do, it doesn't take into account that this assumption may be noisy already. So I assume I can measure a point, let's say, up to 1/3 of a pixel or something like this. But in this setting, have not considered that this information is uncertain, so that I have an uncertainty about the uncertainty of the point. And this becomes such a problem in this setting because I have these high redundancy values over here. If these redundancy values are much, much smaller, then this doesn't play such a big role. But given that I have so many observations, the redundancy gets large, and then assuming that I perfectly know this uncertainty kind of basically will reject these hypotheses all the time. So what I need to do, I need to change the parameters in my F-test to consider that I have uncertainty in my measurement noise. So my measurement noise is not precise. So I have an uncertainty about the uncertainty in the process. So I can still use the same test, so I still use the F-test, but instead of saying, I don't want to say, I know this random variable or the uncertainty of this random variable perfectly, I will say, I need to take a smaller value in here that allows me to encode an uncertainty that I have about how accurately I can actually measure my points. And so the good thing, there's direct relation, at least an approximation for a direct relation between this redundancy value that I need to put into the F-test and the standard deviation about the variance about the standard deviation of how accurately I can measure points. So what I can now do is I can fix my example and I take the same values that I had before, but I say I have an uncertainty in this estimate, let's say of 0.2. So simply I can do some tests and say, for example, I have my feature extractor, I have corresponding points, I perfectly know those corresponding points in the scene, and I can check how accurately does my feature detector actually nails down those corresponding points. So I actually get an idea about the uncertainty and maybe also get an estimate of this uncertainty here. Then I can take this value and put it into the equation we had before, put them into this equation over here, and then I get an R0 value of approximately 13 just by putting this value in here. So I simply apply the F-test with a different parameter, and if this parameter is smaller than the uncertainty, it basically means that this parameter here is noisy. So my assumed uncertainty of my measurements. And if I then can do a statistical test with this, this is typically accepted, saying that if my variance factor was slightly varying, I get so in this case, a 1.36. I still have a correct model.
Why again do you have infinity down there under the
yeah, that's a copy-paste mistake. I'm very sorry. 13 should go here. Should go in here. I'm sorry. before, yeah, it was copy-paste from this slide, and then just the formula was corrected. So this should be the 13 over here. Sorry for that. Okay, so the key thing is that I can take the variance factor into account to estimate how well do my assumption match what I actually obtain. And this F-test, not assuming that my measurement uncertainty is perfect, is essential in order to make an appropriate evaluation of the result. Otherwise, the null hypothesis will always be, or the hypothesis will always be rejected that it will always say that the variance factor is too far away from 1 to have a good estimate. Once I have this variance factor, I can actually estimate the uncertainty in my parameters by relating the uncertainty in my observations through the standard equation with the uncertainty I have in my parameters. And if there are no or just a small number of gross errors in my observations, especially given that I have a large number of observations, this is typically a realistic estimate of what I'm going to obtain. So I can, if I have a large number of observations, I'm free of outliers, the precision that I actually obtain is a realistic estimate of the results that I actually computed. And if you kind of put a lot of those things together, and one example of one of the systems, or recently published system, which does the pose estimation and mapping at the same point in time using camera images on a car data set. So this is one of the standard data sets used for evaluating motion tracking in cars. What you can see here is the camera image, the single camera. These are special features extracted from the environment. The goal is here that they are very robust features. And what you see down here is, so this is the estimate of the car, and those black points are the points we already mapped. The red points are the points we are currently seeing. And you can see how the car drives around through the scene and builds up a model of the environment and the location, estimates the location of the car. The important thing is this is one of the techniques which combines a lot of outlier rejection techniques and does all these things online. So you don't have to wait long anymore in order to do that. So you directly get an estimate. What important is here you get a mismatch between the trajectory estimates. And at some point in time, the system waits a little bit until it can make a good data association, not just between one images, but between a sequence of images, and then can make the correct data association between those points, integrates it into the map. And you saw this correction of the map, which was there labeled as loop closure, which leads to where the least squares approach, which is executed after every frame or nearly every frame, actually provides a correction of the map. Here you could see it again. So the map kind of snapped back because you get new observations, which is relating the current observation with observations you obtained previously, which allows you to do these corrections. And so ORB-SLAM is one of these techniques published in the beginning of the year, which you can actually download as open source software developed by the University of Saragossa, and which is one of the modern standard visual SLAM techniques, which builds this system, or which builds a map of the environment just by estimating the location of the features in the environment and the estimation and estimating the location of the car in the scene. And again here, so the features that you see here, they are rather sparse, so there are not many features in the images, but they're extremely robust. So you see that there are no features popping up and being eliminated again. So these features are comparably stable. And then in the end, you can do a final reconstruction of the environment based on this visual information. So this is what techniques or modern techniques can actually do in estimating the position of the camera, of the sensor, in this case the platform, and the position of the point in the 3D world. And then you can actually use those points when you reobserve them to localize in the existing models. So that was it from my point, from my side for today. We haven't looked into kind of how we solve the bundle adjustment system. We just built up our system of linear equations. We said if we solved it, we have an idea on how precise our results are, and we have some idea on how to deal with with gross errors, how to eliminate gross errors, how to obtain an initial guess. And what we're going to do next week is look into how can we actually solve this large system of linear equations and what should we do, which technique can we apply in order to solve that efficiently. That's it from my side. Thank you very much for your attention, and we'll see each other next week. Thank you.